Let's resume. In the previous video, we talked about the law of sines, and then we talked about some applications, namely solving triangles. The most important and the most typical case was the first case, when all three angles are known or can be readily calculated and one side is given. And this case will serve as a base case for all the application problems we are going to discuss here in this course. Here's one such example. A pilot is flying over a straight highway. He determines the angle of depression of two mileposts A and B that are 5 miles apart to be 32 degrees and 48 degrees as shown in the figure. Find the distance of the plane from the post A, and then find the elevation of the plane. Okay, here's the solution. And by the way, here is a simplified version of the picture there. Let's call the cockpit of the airplane as C. Then we have triangle A, B, and C. And small c here, the length of the side capital A to capital B, that's 5 miles. And the angle capital A is 32 degrees, and the angle capital B is 48 degrees because, the angle capital A and the 32 degrees are alternate interior angles, and they are the same if you have parallel lines. And the 48 degrees and the interior angle capital B, again, are the same because they are alternate interior angles. Well, you can easily see those from those parallel lines, even though you don't remember the names. Anyway, capital A is 32 degrees, capital B is 48 degrees. So summing them up and subtracting from 180 degrees, you can easily find out the angle, interior angle C on top. Turns out 100 degrees. And the opposite side, is 5 miles. So what do we have? From law of sines, we can find out sine of capital B over small b is equal to sine of capital C over small c, and we are looking for b value. That's the distance between the cockpit and milepost A. And solving it, and then punching the calculator, you get about 3.77 miles. Now, how about the height? Well, if the height is h, then we have a right triangle. As a matter of fact, all we have to do is to look at the left-hand side half, a left-hand side right triangle. Then sine of capital A is h over b, so h is b sine of capital A. You can easily figure it out because you just found out what b value is from the previous problem. And then use the angle capital A this time, and you get about 2 miles. That's the altitude of the airplane right now. Okay, let's move on to the next problem. This problem is going to be a little bit more challenging because we do not see the right triangle right away. A tree on a hillside casts a shadow of 215 feet down the hill. If the angle of inclination of the hill is 22 degrees to the horizon, and, sorry about the typo, the angle of the elevation of the sun is 52 degrees, find the height of the tree. Well, you can easily see the triangle forming, but then again, well, how do you figure out the angle? Well, as a matter of fact, it was a bit inadvertent, but I kind of gave away the answer before explaining this problem. I used the term right angle or right triangle somewhere, and I regret it now. That was too much of a hint. Well, okay, here it is. And here is the simplified version of the problem. Capital A is the tip of the tree, capital C is the base of the tree, capital B here is the tip of the shadow. And then the distance between the base of the tree and the tip of the shadow is about 215 feet. Yes. And the angle of inclination was 22 degrees for the hill and 52 degrees for the sun. Yes. And that gives us the difference between the two, 30 degrees as the internal angle, capital B. And also, well, where do we use the right triangle here? Well, we used it already once, getting the 52 minus 22, but one more is about to come. Let's see. Please note that this triangle, the right triangle obtained by extending AC, we have the right triangle here, so the internal angle capital A is equal to 90 degrees minus 52. We end up with 38 degrees on top. Now that we got one angle, 30 degrees, and the second angle, 38 degrees, we can find out the third angle, subtracting the sum of the other two angles from 180 degrees. We get 112 degrees. That's capital C. So what we have? We have all three angles, and then one side, small a, is known. And we are looking for, well, small b. So let's find out. Sine of capital A of small a is equal to sine of capital B over small b. You can find a small b value. That's the only unknown value from this equation. And here we go. We end up with 175 feet. That's pretty large tree. Okay, how much time do we have? Okay, I guess that's sufficient time to do problem C. Okay, let's go. A water tower 30 meters tall is located on top of the hill. On top of a hill. Another typo, sorry. From a distance of 120 meters down the hill, it is observed that the angle formed between the top and base of the tower is 8 degrees. Find the angle of the inclination of the hill. So again, we have to find out the angle of the inclination. So just like the previous problem, you will have to form a right triangle by drilling through this top of this hill, imaginary of course, imaginary drilling of course. Eventually you end up with this right triangle inscribed like this. This is a simplified version. That's the given picture, and this is a simplified version. Not only that, it is it is plotted up to the true scale. Let's go back with 8 degrees of the difference of the angle of inclination. Let's go down. Okay, 8 degrees. And the angle of inclination of the hill, in this case, is capital I. That's what you're looking for. And in this triangle, one side 120 meters, actually, excuse me, 120 meters and 30 meters, those two are given. So 120 meters, that's small a. Small b, 30 meters, those are given. Now we have to find out capital I. In order to do that, you have to find out that capital A, the internal angle of capital A, the top angle. Why? Well, look at the right triangle, and I plus 8 plus A, the top angle, plus 90 degrees turns out to be the sum of the internal angles of triangle, so it's 180 degrees. So we end up with this result. This angle of inclination is 82 minus A. So if you find out A, capital A, then you can find out I, the angle of inclination. All right, let's find out capital A, and we can do that through the law of sine. Small a is 120 degrees, small b is 30 meters, capital B is 8 degrees. So all I have to do is form this equation. Everything is known except for the numerator, sine of capital A. So find out, and turns out sine of capital A is 0.55 something. Take the arcsine, what do you get? 33.8274 degrees. We don't have to worry about 180 degrees minus of that, because that's obtuse angle. That doesn't make any sense. Consequently, the angle of inclination I is 82 minus of that. We end up with approximately 48.2 degrees. Okay, we went through 3 application problems. The last one was pretty hard. Now I think we are ready to prove this theorem, law of sine. Okay, let's go ahead and do that. Here we go. We have a triangle ABC, and we begin with drawing a vertical line from top point A, and we have R, and H is the height of the triangle, as you can see in this picture. Now what you need to do is to look at 2 right triangle, left hand side and the right hand side. In the left hand side we have the angle capital C, and then hypotenuse small b. Consequently, what we have, H is H over B is equal to sine of capital C, and consequently we get B sine of C is equal to H. Now if you look at the right hand side, right triangle, then we have angle capital B and hypotenuse is C, and H is the opposite. So by the same argument we have H is equal to C sine of B, like that. Setting these two equal, B sine of capital C and C sine of capital B equal to each other, we get this one, B sine of capital C is equal to C sine of capital B. Dividing both of them by BC, we get the desired result. Sine of capital C over small c is equal to sine of capital B over small b. If you repeat this process with other direction, then you're going to get sine of capital A over small a is equal to sine of capital B over small b, and also sine of capital A over small a is equal to sine of capital C over small c. Put those all together, then you're going to get the desired result. Now what if you have an obtuse triangle? Okay, keep giving acute triangle. Okay, kind of like this. Is it going to be different? Actually, not really. And we have the left hand side, we have the triangle. We still have h of b is sine of c, because you see c is an obtuse angle, but still okay because b is the radius and h is the vertical. So b sine of capital C is h, that stays the same. And the big triangle is a right hand side triangle, triangle AB capital R, and that gives you h as the opposite, c is the hypotenuse, so h equals to c sine of b. What do you get in the end? B sine of capital C is equal to C sine of capital B. So we have the same result as before.